Hello, this is Ilianos. I'm a physics teacher with ATS in Align, and in this video we'll try to solve the 2022 exam for AP Physics Electromagnetism. Actually, more specifically, we'll try to solve the second question of this exam. As we have the exam paper and we scroll down, we see the basic constants and the unit symbols and prefixes and the basic formula that we need for our exam and a few tips for calculus and geometry. Now, in the previous video we solved question 1. In this video we'll proceed to question 2, where unfortunately we don't have a diagram here. However, we have a battery, a voltmeter, a resistor, a capacitor, a variable capacitor and a switch. And we need to use these symbols in order to draw a diagram that shows how we can charge the capacitor or how we can discharge the capacitor through the resistor. So again, we're going to use the battery somewhere. Now there are a few ways that we can draw this diagram. One way, what I like to do is if we consider that the switch is here, I will have my capacitor somewhere here. This is a variable capacitor. I could try to draw it a little bit better. So here is my capacitor, and it is a variable capacitor. So there is an R over there. Now, right now, my capacitor is, if we close the switch, the capacitor will be charging, and in order to discharge it, we can connect a resistor somehow like this, with one more switch that looks approximately like this. Now I think I made a small mistake here. Now if I close this switch, indeed the capacitor is charging, but there's no way to discharge the capacitor, so I will move the switch from this position. I will close the circuit here, and I will put the switch somewhere here. Now, in this way, if we close the switch, the capacitor is charging. When we open the switch, the capacitor has a constant charge. The capacitor stores this charge, and when we close this switch, then the capacitor is discharging through the resistor. I also forgot to use before actually we draw the voltmeter, I need to check if I have the liberty to use more than one switch, and indeed he gives us that I can use more switches if I need. This actually gives a hint that probably we need to use more switches anyway. And what I forgot is the voltmeter. I need to check where we need to put this voltmeter to study the potential difference across the capacitor. So this voltmeter should be connected in parallel across the capacitor, somehow like this. So more or less, this is the diagram. Again, there are a few variations of this, but we'll proceed with this drawing. Later, and when the capacitor is fully charged, the capacitor starts discharging, so we close the second switch and we open the first switch at the same time, and we need to show that the potential difference will be given through that rule. Alright, now we don't need to draw a new diagram. However, I will use this part of the diagram, and I could remove the voltmeter just to show that the capacitor discharges. So when we close the switch, current will be flowing to the opposite direction of the battery than before, and this current is a variable current, so I'm drawing with a small I, and the charge will be varying with time, and also the voltage of the capacitor will be varying with time. Now, one way to actually calculate the charge or the voltage or the current is Kirchhoff's loop law. Now, although this is for part B, I'm going to write it on the top. Kirchhoff's loop law states that summation of the voltage, summation of the EMF minus summation of the current times the resistance is equal to 0. Now the only voltage that we have here is the variable voltage of the capacitor, so I'm saying voltage of capacitor as a function of time minus current as a function of time times the resistance R. And if we remember the definition for the capacitance is Q over V, so the voltage of the capacitor is Q over C, with this Q being a function of time. So we have Q as a function of time over the capacitance minus the current as a function of time. Its definition is dQ over dt multiplied by R is equal to 0, and from this we bring that the dQ, charge as a function of time divided by C is equal dQ times R over dt. Now what I forgot, sometimes it happens, is the following. Let me try to point it out somehow. We have, now the current is opposing the current as the capacitor was charging. So somehow I need to show this. So actually what I should have done is this current is opposite to the initial one. So we have an opposite sign here and an opposite sign here. So now we have a differential equation. Let me erase this part and bring this to the top. We have a differential equation for the charge of the capacitor. The basic way to solve complicated differential equations is the separation of variables. So we need to have the q's somewhere together on the right side. So this means that we'll have minus dq over q as a function of time, and it will be equal dt over rc. And actually I'm going to bring the minus to the other side, so this is equal somehow like this. And in order to cancel the derivative, I need to antiderive, so antiderive here and there. Now the first integration is very easy, minus t over rc. The second integration is integration of 1 over x, so it is ln of x. However, I'm going to write ln of q. However, for the time, we need to say from time that it is a variable to time, actually from time 0 to time that it is variable. When the time is 0, we don't really need this bracket, but we have not the same conditions for the charge. The charge at the beginning was the maximum charge, or the initial charge QO, and we need the charge as a function of time, so to a small q. So what this brings is minus t over rc equals ln of q minus ln of q max. I'm going to write for the moment QO. Now the difference between the ln's is ln of the ratio q over QO. In order to cancel the ln, I'm gonna say e to the power of minus t over rc is equal q as a function of time over QO. So the charge as a function of time is QO multiplied by e to the power of negative t over rc. Now, we don't have exactly the function that we need, but we remember that the capacitance is charge over voltage. So in the equation that we have the right to multiply, or actually divide by the divide by the capacitance. And from this we bring the voltage. So the voltage of the capacitor as a function of time is equal to the initial voltage delta V0 multiplied by e to the power of minus t over rc, which is what we need to prove. So part B is also done. We continue to part C, where we have a graph of the ln delta V over delta C. My case is that I will need to use the equation that I proved before. So let's bring it somewhere here. And we have a graph of the ln of delta V over delta VO with respect to time. And we need to draw the best fit line. Now, if we zoom in, we need a line that connects all these points, and a few of these points will be above the line, a few of these points will be below the line. I think that what I've drawn right now, more or less, is correct. Maybe I need to modify and bring it a little bit higher. Somehow like this. This should be enough. So this is more or less the best fit line. And using this best fit line, we need to find the value of the capacitance. Now, let's bring the equation that we proved before. We said that the delta V over, the delta V as a function of time is equal to delta V O times e to the power of minus t over RC. And again, we need to create the ln. So first I'm going to divide delta V over delta VO is equal minus e to the power of negative t. Actually, there is no minus. E to the power of negative t over RC. And if we ln left and right, we bring that the ln of delta V over delta VO is equal minus t over RC. So what we get is, our value on the y-axis, which is the ln, the value on the x-axis, which is the t, and the coefficient. So this becomes ln of delta V over delta VO is equal minus 1 over RC multiplied by the t. So more or less we have a linear relationship, y is equal a coefficient times x. And we need to find the value of the RC, and for this we're going to use the slope, which is y over x, or rise over run. So we need to say that minus 1 over RC is equal to the value of the slope. So this is very, very important to be mentioned. And somehow we need to make sure that we mention what is the value of the slope. The slope is rise over run. And we need to find 2 points that belong exactly, that we can find its values exactly what is the value of x and what is the value of y. Now, I will need some time for this, but one point that I see clearly the value for, is this, and one more point that I clearly see the value is that. So from this we can bring that the slope is equal minus 0.6 minus 0.2, so minus 0.6 minus 0.2 divided by the value of on the x-axis, which is 0.45 minus 0.15. 0.45 minus 0.15. Now straight to the calculator, so negative 0.4 divided by 0.3, this is negative 1.33, and we can use this in order to find the value of the capacitance. So minus 1.33 equals minus 1 over the resistance, I believe it is given, 150 kilo ohms. So 150 times 10 to the power of 3 multiplied by the capacitance, and from this we bring that 1.33 times 150 times 10 to the power of 3, and we need the inverse value of that, so 1 over the answer, it is approximately 5 times 10 to the power of negative 6 farad, or you can say that the capacitance is 5 microfarad. which is our final answer. Now we can move on to part D, where we need to mention what happens to the slope if the surface area of the plates is increased. Now, we need to remember that the capacitance depends on the area, the surface area of the plates of the capacitor, and if I remember correctly, C is equal epsilon 0 multiplied by the area divided by the distance. So, if the area increases, the capacitance will also increase. So, in other words, it is mentioned that the capacitance increased, and the capacitance is increased. And we need to figure out what's happening to the slope of this graph. For this reason, I will bring this part of the formula, so ln of delta V over delta V, O is equal minus 1 over RC times the T. Actually, we said that the slope, I should have brought that part of the previous solution, so the slope is minus 1 over RC. It is clearly given that the capacitance increases, so since the slope and the capacitance are inversely proportional, it means that the slope will be decreasing as a value. Since the slope decreases as a value, this means that it will become less steep. So this is what we need to mention, is that on the previous part we proved that the slope is equal to minus 1 over RC. So since the area increases, this will bring a change in the capacitance. The capacitance also increases, and the capacitance and the slope are inversely proportional. So we need to mention this. The value of the slope decreases, and this means that the slope becomes less steep. And on the next part, part E, when it is mentioned that the ideal battery is replaced by a non-ideal battery with internal resistance, what effect this will have to the slope. This is a little bit tricky, I think, but we also said that the slope is equal minus 1 over RC. Now, a little bit careful, this R had nothing to do with the battery. This R was the value of the resistor. So it doesn't matter, although the internal resistance of the battery will affect the charge on the capacitor, this will have nothing to do with the way that the capacitor discharges. So the way that the capacitor discharges only is affected by the resistor. So this resistance R will play no part in the way that the capacitor discharges, so the slope of this graph will not change. So we need to say that this R is the resistor, and it is not affected, the slope is not affected by the internal resistance R. And at the same time, what would the vertical intercept of the graph be in this experiment? Again, the graph itself will not be affected at all by the existence of this small resistance R, but in this case we need to mention the full form of the rule, I believe. So the ln of delta V over delta VO is equal minus 1 over RC times the T, if I'm not mistaken. So again, this R again is the value of the resistor, and it is not affected at all by the internal resistance, so nothing will change in that graph. I think this is the last part. Yes, we're going to part 3 after this. You can stay tuned in order to check the solution to part 3. If you have any comments, feel free to write them. I would like to see your comments on this. I hope you enjoyed the solution to this, and keep studying for every lesson that you have, and the most important of them all, which is physics. Have a good time, and see you soon. Take care.